So today we're going to take a quick look at some important transistor parameters, quantities, and then get into operating regions and a couple of examples. Okay. First up is the junction breakdown voltages. In a BJT, we have two back-to-back PN junction diodes, whether it's NPN or PNP transistors, right? So if we reverse bias these junctions, they will break down similar to any other PN junction, okay, any other PN junction diode. The difference is, as we've seen in the lab, one of the junction breaks down at a lower voltage. It's typically less than 10 volts. And the other one and I'm going to exaggerate the slope. I would say greater than 100 volts, but that's, I would say approximately 100 volts. But it could be anywhere above 50, depending on the fabrication. Okay. So whether it's an NPN transistor or PNP transistor, both of those have two PN junctions. If you reverse bias those junctions, they will break down. The emitter junction or the emitter base junction breaks down at lower voltages because the emitter is very heavily doped, so you have a Zener effect. And the collector base junction will also break down, but it's in excess of 100 volts or so. Okay. And we are not doing anything of that sort in our lab. So next week, when we are done with lab 8, if students wish, we'll go ahead and reverse bias up to the maximum value that we have in the lab. I think we have what, 30, 35 volts DC supply. We'll go ahead and try that, see if it breaks down. All right, so this would be the emitter base junction. And this would be the collector base junction. And this is, of course, the first step in the lab where we try to determine which terminal is the collector and which terminal is the emitter. Okay, so that's the reverse, so junction breakdown voltages. Okay, and of course, the BJT is not a symmetrical device. That's why these reverse bias characteristics are different, right? Okay, then we have a quantity known as the base transit time. Now, the principle of operation of a BJT is you have an emitter, you have a base in the middle, and you have a collector. The emitter will emit the charge carriers. The charge carriers cross over into the base junction. And from the base, they are injected or pushed into the collector. And then they are swept up in the terminal because of the reverse bias applied to that collector terminal. So the time it takes for the charge carrier to start from the emitter, transit through the base, and reach the collector is known as the base transit time. And this parameter is important for two specific reasons, which I'll just talk about in a minute. The base transit time is noted by tau f. Okay, so as the forward transit time, tau f. And tau f can be given by WB square over 2Vt and mu n. WB is the width of the base, so base width. Vt is the thermal voltage. And mu n is the carrier mobility. In this case, we are referring to an NPN transistor. And so it's electrons. So it's the electron mobility. For a PNP transistor, same equation, but mu n is replaced with mu p, the hole mobility. Okay. Now, if you think back to chapters 1 and 2, where we talked about electron and hole mobility. Remember, electron mobility has higher than hole mobility. Mu n has a value that is more than twice the value of mu p. So if you have a device where the charge carriers are electrons, it's going to be twice as fast as a device where the charge carriers are holes. In NPN transistors, charge carriers are electrons. PNP transistors, it's holes. So this is the reason why NPN transistors are faster than PNP transistors. Okay, does that make sense? For the same physical design, in the same fabrication process, an NPN BJT will be faster than a PNP BJT because the primary charge carriers are electrons, which have higher mobility than holes. Yes.
Like significantly faster or only just a small?
No, it's a significant difference. Yeah. Yes. Chapters 1 and 2. I would point you there. Essentially, electrons are free to move about. Holes by itself, if we are going back to the basic, holes by itself are treated as a particle, but hole is an absence of an electron. So a hole is created when an electron moves out of its spot and goes to another spot, right? And so holes are in response to an electron moving out. Okay, and that's one of the reasons why electrons will have a higher mobility than holes. Okay. Also, second, this also places the transit time places a limit or an upper limit on the frequency that can be applied to a BJT. If the transit time is it's higher than the frequency that is being applied, the BJT will not be able to respond to the AC signal. Okay. So high frequency AC signals, which have time periods that are smaller than the transit time, will cause the BJT to not respond in time. Okay. And so that places an upper limit and the operating frequency. And that is given by equation 1 over 2 pi tau f. Okay. Now, when we apply a input, charge is stored in the base. Charge carriers move through the base. Every time the applied voltage changes, the stored charge in the base changes. So that stored charge and the applied, in terms of the applied input voltage, can be modeled as a capacitor. And that capacitor is known as the diffusion capacitance. So diffusion capacitance can be modeled as a capacitor between the base and the emitter terminals. Okay, and that is given by CD equal to IC or tau F times VT times tau F. Capacitance are typically unwanted in circuits because they slow down the operation of your device. And then let's talk about beta cutoff frequency. Now, so far we have always referred to beta as a constant, right? It's a parameter of the BJT due to the physical construction of the BJT, right? But that is only valid at regular lower frequencies. If we were to plot the beta current gain for a BJT as a function of the frequency or the input frequency, it will remain constant up to a certain level and then start to gradually drop off with increase in frequency. So we can write an expression for beta as a function of frequency. This would be Ft, and this would be F beta. And beta as a function of frequency can be given by beta F, the forward current gain, divided by root of 1 plus F over Fp square. So ring a bell from Bode plots for high pass and low pass filters, transfer function of high pass and low pass filters. Actually, that's not Fb, that's F beta. And F beta itself can be written as Ft over beta F. Ft is an important quantity. It is the frequency at which the forward active gain drops to 1. We are talking about hundreds of megahertz. Okay. So if you keep increasing the input frequency, at some point, the current gain of the BJT is going to drop to 1. And that frequency is known as Ft, unity gain frequency. And that divided by beta F gives us F beta. And the transfer function for beta as a function of frequency is here. And so high frequency circuit design is a whole different area of study. And then one last parameter is transconductance. And transconductance GM is the ratio of the output current to the input voltage. Conductance, of course, is the inverse of resistance, so it's current over voltage. Trans in this term means it's a transfer characteristic, so the transfer and transconductance is the change in the output voltage in response to change of the, is a change in the output current in response to the change in input voltage, hence IC over VBE, and the values are taken around the Q point of the circuit. Okay. So at the Q point of the circuit. So early effect and early voltage is named after James Early. He was a scientist and researcher working for Bell Labs. When he was working with the output characteristics of a BJT, he noticed that a slope would occur at higher voltages of VCE. Okay, so these are not typical values. These are highly exaggerated. Okay, these are highly exaggerated. If you recall, when you took collector characteristics for the common emitter amplifier, for higher voltages, for lower currents, so for lower currents, it was a near horizontal line. So like 5 microamps or 10 microamps, it was near flat. But as you went higher up in the input current, meaning the input voltage is now increased, the slope started increasing. Did your lab groups have that kind of, observe that kind of effect? Most of you would have. There were one or two where the slope was not as pronounced. And the reason is we didn't go much beyond 10 or 12 volts. If we go VCE like 13, 14, 15, 16, 20 volts, you can see a more pronounced effect. And so the slope increases as the input voltage increases and the collector emitter voltage increases. So James Early noticed that if he extrapolated all those curves onto the negative axis, they all seem to converge at one single point or around one single point. I wouldn't say exactly at the same point, but around one single point. That voltage came to be known as the early voltage. And the effect that he noticed came to be known as the early effect. And the reason for that is this, is known as the base width modulation. Base width modulation. Now what happens is we are forward biasing our emitter junction and we are reverse biasing our collector base junction. What happens when we reverse bias a PN junction? What happens to the depletion region? It expands, it increases, right? And so when the depletion region, this is the original width right here for the depletion region. And then it expands into the collector and into the base. The base itself is very thin to begin with, right? The collector is very lightly doped, so there are not a lot of charge carriers that are present in there. So when the depletion region increases, it extends into the base region, and the very thin base region has now shrunk even further. And when that happens, transit time, everything changes. The transit time decreases, collector current increases, and because collector current is increasing, you see this exaggerated slope right there. If the collector current didn't increase, you would have a flat line like an FET characteristic. Okay, so the base region shrinks, collector current increases, and we see the early effect. The reason it's important is because the output resistance increases because of the increase in the collector voltage. Okay, and that is a consideration when we want to design an amplifier that is going to drive an output load. So early voltage is defined as the value of VCE on the negative axis, so it's minus VA because of the increase in the collector current, it reduces the output voltage, and hence it places limits on amplification or the amplification factor of the BJT. Collector current is inversely proportional to the base width. So if base width decreases, collector current increases. All right, so these are some of the important parameters that we have to keep in mind when we are working with BJT circuits. All right, we haven't taken a pause, so let's take a, well, then let's move on to, these two slides shouldn't be in there. They should be there. So we already discussed the different operating modes. The reason I bring this up is because before we solve the examples, I just want to show how the voltages are related to each other and how we can determine the region of operation based on the values of these voltages. Okay. So if both junctions are reverse bias, we know the transistor is in cutoff. If both junctions are forward bias, the transistor is in saturation. And if emitter base is forward bias and collector base is reverse bias, then it's in active mode. So when we are trying to determine the operating region or operating mode of a BJT, we look at the voltages, we determine the voltages, the relationship between the voltages, and then determine which junction is forward bias and which one is reverse bias. These are all NPN transistors. It's NPN. And that is the collector, base, emitter. So if it's an NPN transistor, that means the base voltage must be lower than the collector and the emitter voltage, meaning VB must be less than VC and VE. Okay, VB must be less than VC and VB. It's an NPN, meaning the P-type material has to be at a lower voltage than the N-type material. So the base voltage VB must be less. That's the first indication. Forward bias, completely opposite. Base voltage is higher than the collector and the emitter voltages, then both junctions are forward bias. And then, of course, the last case is where the collector voltage is higher than the base voltage, so then it's reverse bias. And then here, the base voltage is higher than the emitter voltage, and then it's forward bias. When we are trying to determine the operating regions, the first thing we check is VBE, or the base emitter junction. If the base emitter junction is reverse bias, meaning the emitter to base voltage is larger than 0.7, then the transistor is in cutoff. We don't need to check anything else. Okay, there is no other option. The other option is reverse active mode, which we'd never ever see, right? Especially when we are doing theoretical studies, we never ever see reverse active. And even if it was reverse active, meaning the emitter base is reverse bias and the collector is forward bias, nothing would happen. The transistor is still off, pretty much. It's not a symmetrical device. So the transistor is pretty much off. Okay. So if the emitter base junction is reverse bias, transistor is off, it's cut off, nothing further. Now, if it's forward bias, then we have two options. We can test for either saturation or active. Okay. So let's look at an example. So we are given a BJT, 3 resistors, 2 voltage supplies. All the values are given to us. We don't need to determine anything except the region of operation. Okay. So VBB is given as 4 volts. VCC is given as 12 volts. V1, which is the voltage at the base, is 2 volts. This is 1.3. And this is 4 volts. The 2 and 1.3 is a clue right there. So all the voltages are given to us. All we need to do is figure out the relationships between the 3 terminals. Okay, so let's begin. What do we have? We have VB as 2 volts. We have VE as 1.3. The first thing we need to check is the base emitter junction. So we want to find VBE. What is VBE? VBE, simply VB minus VE. In this case, 2 minus 1.3. That gives me VBE as 0.7 volts. If VBE is 0.7, it means it is the forward bias base emitter junction. It's the diode voltage drop, 1 forward voltage drop for PN junction diode, 0.7 volts. Right? And so if it's 0.7 volts, we can say base emitter is forward bias. So not cut off, it could be either active or it could be in saturation. Make sense thus far? Forward bias, so not cut off. Now we can either test for saturation. Yes. So a question being asked is, should we consider VBB in calculating these voltages? Not really. So the purpose of this example is that we just directly determine the region of operation. So there are equations and calculations we can perform, and those calculations will show that VB is 2 volts due to VBB being 4 volts. If VBB changed, then VB would change. So in this example, I'm not showing the previous calculations, but we will do that in the next example. So let's see. Where was I? Oh, so it's not in cutoff. The only other option is active or saturation. We'll test for that. If VBE was larger than 0.7, anything like 1 volt, 5 volts, 6 volts, what would that mean? it would be reverse bias. I didn't mention minus. But if it was larger, if the magnitude was larger than 0.7, then it would be reverse bias. Okay. And of course, the negative sign would also be an indicator. All right, let's test for active. So we'll check the collector base junction now, and we'll find the voltage VBC. So you want to find VBC because if that junction is forward bias, that means it would be in saturation. If it's a negative value, meaning it's a reverse bias, that means it's inactive. So VBC would be 2 minus 4, gives me a negative value. Hence, collector base is reverse biased. Hence, active mode and not saturation. Either active or saturation. But let's test for saturation anyway. To test for saturation, remember BJT saturation is on the left side, close to the y-axis. So VCE would be less than or equal to 0.4 volts. Typically, it would be around 0.2 or less. But again, if it's 0.4 or less, then the transistor would be in saturation. So VCE is VC minus VE, which comes out to be what? 4 minus 1.3. 2.7 volts. Hence, not saturation. Okay, let's take a pause. Let me know if you have any questions. Yes. Well, the transistor goes into saturation or is in the saturation region, VCE would be less than 0.4 typically. If you look at the characteristics, transistor characteristics, right here. Typically, it's around 0.2 or so, but it could be up to 0.4. So we say if it's up anywhere less than 0.4, then it's operating in saturation. VC is increased, then it's an active region. So VC sat 0.2 to 0.4 or less than that. Okay, so that is it for this one. Let's look at an example where voltages are not given to us. We have to analyze the circuit, or we must analyze the circuit, determine the voltages, and then perform our analysis. So in this case, we have a BJT given to us. We are asked to determine all BJT voltages and currents, and beta F is given as 125. So VB, VE, VC, IB, IC, and IE. So we have two power supplies. We have VCC and VEE, +5 and -5. RC and RE values are given to us. The base is connected directly to ground. So from inspection, I can directly write VB is 0 volts. VB is 0 volts. Then I see that the emitter is connected to a negative supply via RE, but still connected to a negative supply. So my assumption at this point, I don't know whether it's active cutoff or saturation, but my assumption for this junction is that the PN junction base to emitter is forward bias, because base is at 0, emitter is connected to -5. NPN transistor again, PN junction is forward bias. So I would assume base emitter junction is forward bias. And therefore, I can write VBE is equal to 0.7. It may turn out that my assumption is incorrect. I don't know. We won't know until we finish our analysis and obtain values. Okay. But again, we need to begin at some point. And so our beginning point is that the base emitter junction is forward bias. So if VB is 0.7, and VB is and find VE, right? VE would be minus 0.7. And once you have VE, you can apply Ohm's law here to find IE. No, wait, I have it the other way around. -5. Yeah, no, correct. VE. So this 0.7 plus 5. That gives me 1 milliamp. Okay, 1 milliamp. So you have to keep in mind all the devices that we look at, whether it's diode or FETs or BJTs, everything is analyzed with the same circuit laws, like nodal analysis, Thevenin equivalent, KVL, KCL, mesh current analysis. The techniques don't change. Okay. The only thing that changes is the models. Okay, so IE is 1 milliamp. Now that we have IE and we have beta, we can calculate IC. From beta, we can calculate alpha. From alpha, we can calculate IC. And from IC, we can calculate IB. Okay. Once we have IC, we can apply Ohm's law again to RC and calculate VC. And thus, we have all those voltages. All right, so let's calculate IC first. Alpha is beta over beta plus 1. So 125 over 126 comes to 0.99206. Milliamps, 0.992 milliamps. And we apply Ohm's law to RC. I can write IC is equal to VCC minus VC over RC. So minus VC is equal to IC RC minus VCC, 0.992 times 2000 minus 5. And that gives me VC as equal to, what do you obtain? Approximately equal to 3 volts. So now we have VB, VE, and VC. Our assumption was initially that base emitter is forward bias. Now we can look at the collector base junctions and determine if it's forward bias or reverse bias. Okay. And so we look at the collector emitter junction. We find VCE, VC minus VE. And 3 minus of minus 0.7, so 3.7 volts. So VCE is much larger than 0.4 volts. Not saturation. And we can also test for active as VBC. If the base collector junction is reverse bias, that is also active mode. Here we tested saturation. VCE is larger than 0.4 volts, so not in saturation. So we test for active. VC minus 3 volts, hence reverse bias. Therefore, active mode. Okay. Does the process make sense? First example, voltage is already given. Second example, we determine the voltages by applying analysis techniques. We find the voltages at the 3 terminals and determine the region of operation based on our table. Okay. All right. Any questions? Yes. That would mean that so if VB wasn't 0.7, none of the other regions or values would turn out to be correct. It would be larger. It would end up being larger than it would just be cut off. Because right now we test it for saturation and we test it for active. Both of them turn out to be true. If our assumption was incorrect, it would show up as in either one of them wouldn't match. I don't have a specific value that I can pull out and show right now, but I've seen examples where assumption would be wrong. And so if you test for saturation, maybe it turns out to be correct, but it tests for active, it wouldn't be correct. So either one of them would turn out to be incorrect. And that means we would have to go back and change our assumption. Okay. All right, any other questions? Okay, I'm going to assign this as student practice outside of class. RC value of 15 kilo ohm. Shouldn't take longer than 10 minutes, but practice it outside of class. you only need to change not one assumption, one calculation, and then determine the region of operation. Okay. All right, we have a few minutes left, and I just want to discuss BJT biasing. Okay, this is going to be important for next week's lab. So we won't we won't have time to go into everything today, but at least by Monday. Okay, so we've talked about biasing and why it's important. Biasing is applying DC voltages to a BJT to constrain it or to force it to work in a certain region of operation, right? So here are three different kind of biasing circuits. First up, we have the fixed bias, the emitter bias, and then the voltage divider bias. We are not going to go in detail and analyze these. But I just want to point out, we give the input at the base and take the output at the collector. These are all common emitter biasing modes. In the fixed biasing, we simply have two resistors connected to a single supply. It's supplying voltages to the base as well as to the collector. There's analysis we can perform. We apply KVL on the input side. We apply KVL on the output side. And we generate equations. And we can also do a load line analysis. Okay. The drawback of both the fixed bias and the emitter bias is that the equation for the current gain or the Q point is dependent on beta. Okay, the whole point, the entire point of biasing is so that we can fix the Q point to operate in a certain region. Now, if your biasing circuit works for one BJT, meaning one value of beta, and you plug in or insert a second BJT in its place with a different beta, your biasing circuit may not work. Okay, it may not work. Hence, we use voltage divider bias. In voltage divider bias, the Q point is somewhat independent of the beta values. There are, of course, certain considerations to take into account, but we will see those on Monday. Okay, we'll see those on Monday. There will be a homework assignment for the weekend. The reading is already assigned. Quiz on Monday based only on the BJT, and I'll post the announcement about the topics. Also, let's see. Oh, the homework had a error in the calculation of alpha. A couple of students brought it up in the morning session. I will also send me an email about it. Surprisingly, only one student emailed me about it. No one else did. So only adjusted the credit for that student. No one else gets credit. You got to send me an email. Now, I'll make the change in there. The system doesn't allow me directly to make a change in there. So I'm going to send feedback to them that there's an error in the solution. Okay. And I will see how I can adjust the credit for all students. All right. So I'll bid you a good weekend, and I will see you all on Monday.